Today we're looking at 3.3 notes on heat capacity and specific heat, looking at the two outcomes of heat in the Physical Science 20, analyzing qualitatively and quantitatively the effect of heat on matter during temperature changes and changes of state using kinetic molecular theory, and determining experimentally the quantities of heat involved in chemical reactions. And in this lesson, we will learn and compare in quantitative terms the heat capacities of some common materials, including water, and explain how heat capacity can influence choices of materials used in the development of technologies related to clothing, food, and shelter, as well as calculate the quantity of heat and specific heat to the correct number of significant figures. So, what is heat capacity? Have you ever noticed that some objects heat up quickly while others heat up slowly? The reason for this is heat capacity. Objects that have a high heat capacity will take a long time to heat up, as well as once they're warm, they take a long time to cool down. Water is an example of a substance with a high heat capacity. Objects that have a very low heat capacity will heat up and cool down very quickly. Most metals have a low heat capacity. Specific heat capacity refers to the mathematical way to calculate how easy it is to change the temperature of something. Specific heat capacity is the amount of energy, measured in joules, required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. Some things you should know. There are some sources that define specific heat capacity by the gram instead of the kilogram. The digits will be the same, but the numbers will differ by a factor of 1,000. Make sure you read the units carefully so you don't make this mistake. Some sources use Kelvin instead of Celsius. Since the size of 1 degree in Celsius and Kelvin are the same, this doesn't affect the result. The specific heat of water is 4.18 times 10 to the third joules per kilogram degrees Celsius. And if you note, the specific heat of water is a lot higher than most other common liquids. For example, cooking oil has a specific heat of 2.0 times 10 to the third joules per kilogram degrees Celsius, so about twice as low, which would heat up more quickly on a stove, assuming you've equal masses of each. So water would heat up significantly slower because it has a higher heat capacity. You need to put a lot more energy into heating up water than you do for cooking oil. And specific heat will be used in a lot of calculations involving energy. So we have this formula for the quantity of heat. So since we know how much energy is required to raise the temperature of a substance by 1 degree Celsius, it is now easy to find the amount of energy required to produce a certain temperature change using a simple formula. Q is equal to mc delta T. Q is equal to the quantity of heat in joules. M is the mass in kilograms or grams. We need to make sure we match our specific heat capacity, whatever we get from our table of values or is given to us in the question. C is specific heat capacity in joules per kilogram degree Celsius, or as said, sometimes they can be given in joules per gram degree Celsius, which in that case we would need to make sure our mass was in grams. And change in temperature is in degrees Celsius or Kelvin. And just a note here, whenever you see that change symbol, that delta in temperature, that means your final temperature minus your initial temperature. So if there's a note here, if an object absorbs energy, its final temperature is higher, so its delta T is positive. And if the object loses energy, the temperature falls and its delta T is negative. Therefore, if Q is negative, the object is losing energy, and if Q is positive, the object is gaining energy. Going through our first example here, when 200 milliliters of water is heated from 15 degrees Celsius to 40 degrees Celsius, how much energy is absorbed by the water? So there's a key thing we might want to underline here, how much energy is absorbed. So that's what we're looking for. Amount of energy absorbed talks about Q. Remember, energy is measured in joules and Q is measured in joules. So we're looking for joules as a final, Q as a final answer. And if we look at how many significant figures are numbers that are given, we have 4 in our first number, and 3, and 3. So our answer will need to have 3 significant figures and be in units joules. And if we list the rest of our variables, m, c, delta t, let's try to define these. So it says when 200 milliliters of water, and there's a note, 1 milliliter is equal to 1 gram. So 200 grams of water is heated from 15 degrees Celsius to 40 degrees Celsius, remembering that change in temperature is T final minus T initial. We can say our final temperature there is 40 degrees and our initial is 15. So our change in temperature is 25 degrees Celsius. And our question is asking us about water. We need to look up water on our specific heat capacity table. Now, water has a specific heat capacity of 4180 joules per kilogram degrees Celsius. And if we take a look, our specific heat is given in kilograms and our mass is in grams. So we're going to want to change our mass. So it's in kilograms. If we divide by 1,000, we get 0.2 kilograms. All right. So now we write out our equation. Q is equal to mc delta t, and we plug in our variables. So Q is equal to our mass is 0.2 times our specific heat, 4180, multiplied by 25. And Q, if we plug that into our calculator, we go 0.2 times 4180 times 25. We get 20,900, and our answer's in joules. And if we take a look, our answer needs to be to 3 significant figures and in joules, and our answer is to 3 significant figures and has the units joules. Our next example, a copper pot with a mass of 1.2 kilograms is at a temperature of 120 degrees Celsius. If the pot cools to a temperature of 20 degrees Celsius, how much energy is released into the surroundings? So, let's start by writing out our variables and defining them. So, if we take a look, a copper pot, that's telling us its specific heat capacity, which we look up, and copper is 390 joules per kilogram degrees Celsius. Per kilogram degrees Celsius, and it has a mass of 1.2 kilograms. If we take a look, our units are in kilograms, both our specific heat and our mass, so we're okay there. We don't need to adjust our units of our mass. And it says the pot starts at a temperature of 120 degrees Celsius and it cools to a temperature of 20. So T final minus T initial. It starts, our initial temperature is 120 degrees, and it cools to 20 degrees. So our change in temperature is 100 degrees Celsius. Here. And it's asking how much energy is released into the surroundings. So that's looking for Q. And if we take a look, we have 2 significant figures, 2 significant figures, and 3 significant figures. So our final answer is going to have to be 2 significant figures and in joules. We then write out our formula. Q is equal to mc delta T, and plug in our variables. 1.2 times 390 times negative 100. So Q is equal to, plugging this into our calculator, 1.2 times 390 times negative 100. We get negative 46800 joules. We need 2 significant figures, so we're going to need to round. Negative 47000 joules. Or if you wanted to write that out of in a sentence, you can always drop that negative and say 47,000 joules is released. Because when we have energy being released, that's a negative amount of energy. So either way would be fine to write that, because by saying that there's 47,000 joules released, you're telling me that the numerical value is negative 47,000 joules. Our next example here, a silver teaspoon with a mass of 25 grams is heated from a temperature of 20 degrees to a temperature of 75 degrees. What is the amount of energy absorbed by the teaspoon? Let's write out our variables. Q, M, C, delta T. We have a silver spoon. Let's take a look. Silver is 230 joules per kilogram degrees Celsius. And it says with a mass of 25 grams. And if we take a look, we have grams and kilograms, which means we have to change our grams into kilograms by dividing by 1,000. So we get 0.025 kilograms. We want those units to match, so they cancel out. And our change in temperature is T final minus T initial. And it starts at a temperature of 20 degrees up to 75. So our change in temperature in this case is 55 degrees Celsius. We're looking for our energy. So taking a quick look, we need our answer to 3 significant figures and our answer in joules. So Q is equal to mc delta T, and plugging in our numbers, we have 0.025 multiplied by 230 and 55. Q is equal to, so plugging this into our calculator. Sorry about the little bit of a mess there. It's tough to write on an iPad some days. We get 316.25. joules, And we need to write that to proper significant figures. So which is 3. So 316 joules is our final answer. Our next example here, an unknown substance with a mass of 75 grams is heated by 827 joules. This causes the temperature of a substance to rise from 21 degrees Celsius to 45.6 degrees Celsius. What was the specific heat of the substance? So a little bit different here. Let's be careful. Let's define our variables. So an unknown substance, when saying an unknown substance, we don't know our specific heat. So let's put a question mark in specific heat. Yes, we can also say we need it to 3 significant figures. And our units are going to be joules per kilogram degrees Celsius. Although with saying that, my mass is 75 grams, so I could have left my specific heat in joules per gram degree Celsius, but since I want my units to be in kilogram degree Celsius, I'll need to make sure I convert my mass. So 0.075 grams, and it's heated by 827 joules. That's our, 827 joules. That's really messy. Let's fix that. So that's our specific heat. Sorry, that's our energy, or our Q. Remember, energy is measured in joules. And our change in temperature, it goes from 21.0 to 45.6. So T final minus T initial, we have 45.6 minus 21. So if we figure that out, we have 24.6 degrees Celsius. Taking a look at our equation, Q is equal to mc delta T. This time we're looking for C. So it's good practice to rearrange your formula to, for the variable that you're looking for before you put in your numbers. So I'm going to divide both sides by m and delta T. Then I can cancel those off, and I can get C by itself. So Q over m delta T is equal to C. And remember, I could have just went straight to C is equal to Q over m delta T. Both those two steps are the exact same thing. So if you want to go straight to flipping around that equation, there's no problem with that. And then plugging in our variables, we have 827 over 0.075 times 24.6. C is equal to, I'm plugging this into my calculator here, 827 divided by 0.075 divided by 24.6. We have our final answer of 448. No, it's 3 significant figures. Good. Joules per kilogram degrees Celsius. So if we took a look at our chart, we could probably speculate that it's possibly iron. That's the closest, 460 as a specific heat is what that value is telling us. Although this question isn't asking for what the substance actually is, so we wouldn't have to write that in. Some questions might ask you, what is that substance? And you just pick your closest value. Or there might be a couple closest values, and you write that down as well. And our last example here, 55,000 joules of heat is released. So this is a really important statement here. Joules released, that tells us that we have a negative 55,000 joules. And we need to make sure we make that distinction, or else we're not going to get the correct answer. And when 640 grams of gold, so that's mass, let's change that over to kilograms, 6.064, 0.640 kilograms of gold. There's our, we need to look up gold. 130, it's very low specific heat capacity, joules per kilogram degrees Celsius. And our change in temperature. So if the silver was initially at negative 10 degrees Celsius, what is the final temperature? Oh, tricky question. Lots of things here. So we don't know our final temperature, but we know our initial temperature. So our delta T is T final. So subtracting negative 10, that's plus 10. We'll have to plug that whole thing in for our delta T. So if we write out our formula, Q is equal to MC delta T. And if we want to rearrange our formula, so delta T is by itself, we can go delta T is equal to Q over MC. And then plugging in our value, so remember here, TF plus 10 has to completely go in for delta T. So we need to go TF plus 10 is equal to negative 55,000 all over our mass, 0.64 multiplied by 130. So if we figure out that number on our right-hand side, 55,000 divided by 0.64 times 130, we get an answer of TF plus 10 is equal to negative 661 degrees Celsius. And so we need to subtract 10 from both sides in order to get TF by itself. TF is equal to negative 671 degrees Celsius. Okay. Although we need to write two significant figures, so negative 670 degrees Celsius. Which makes sense in this question because it says the silver was initially at negative 10 degrees. What's the final temperature? And previously it says the temperature of gold drops in temperature. So our final temperature has to be lower. So it's always good to look back to that question and make sure it makes sense to the question. There's also some additional examples. If you'd like me to go through those, please shoot me an email and I'll help you out.